completing his PhD at MIT and his MD at Harvard. He then came to Cornell back in New York for residency, where we were residents together, and then completed enfolded fellowships in endovascular neurosurgery and endoscopic skull-base surgery. As the director of Biodesign, he runs a large program that is designed to pursue rapid innovation and development of surgical technology within our department. And so I'm going to turn over the floor to him to talk about that, and then introduce Joe Borello, our speaker for this morning, before the Hollin lecture.
Thank you so much, Peter. Let me just share my screen here. Is that coming through now on the share?
Yep. Yes.
Great. Well, thank you so much for having Biodesign, and this morning I'm just a warm-up act for the main attractions, but I would like to set the stage for the other talk that I'm warming up this morning by speaking a little bit about the educational work that we're doing within Biodesign, and more broadly across medical education and surgical education in technology innovation across the institution. I do have some disclosures related to my work in Biodesign, but won't focus on that work this morning. Biodesign at its core is an engineering discipline around the process of innovating in medical technologies. I think sometimes innovation is thought of as with a sense of mystique as being based on eureka moments, but the truth is that there's engineering discipline behind innovation, and innovation can be taught. And through work in Biodesign, I really have the privilege of working with a number of colleagues throughout the institution, in our department and in other departments, on translational research initiatives. And that has been a great experience over the last 2 years. As many of you know, these are complex and nuanced relationships and engagements. And sometimes they're exciting, often they're frustrating along the way, as research often is. And they require teamwork, collaboration, and infrastructure. Within this department and across the institution as a whole, I think there is a growing consensus that learning core aspects of device development and interaction with industry should be carefully and deliberately incorporated into the training of the modern academic surgeon. This is really one of the missions of Biodesign, and I think it's a unique perspective, maybe born somewhat out of the New York entrepreneurial ecosystem. And we're in resident interview season, and I said a number of times to the residency candidates that I really think this is a unique aspect of the training that we offer in neurosurgery at Mount Sinai. We have a growing team here at Biodesign. You'll meet one of our stars today. And this team includes faculty, staff, as well as professional engineers, project managers, and trainees. Our current roster of trainees is pretty extensive. We currently support 2 biomedical engineering PhD students, 1 MD PhD through the Mount Sinai MD PhD program, 1 PhD student specializing in device translational development and clinical trials. And I'm very fortunate to have the real privilege of working with a number of residents and fellows in our department and others, as well as very talented medical students. As many of you know, we have a very versatile prototyping center here within the basement of Mount Sinai Hospital. Many of you have been here. And one of the secrets to our success, I really think, is the proximity of the lab to the operating room and the interventional suites. That really promotes a flow of an active flow of hands-on work with surgeons and engineers working together on prototypes and rapid iteration. We also work very closely with Mount Sinai Innovation Partners, MSIP, which is the translational arm of the institution. Many of you have had some interactions with them, and these relationships are key. They're complex, and that's a subject, I think, for another grand rounds another time. We have an almost unable to be counted at this point number of interns and students from around the city and the region who spent semesters or years with us in Biodesign. Here are some of our past students, undergraduate and master's level, from Cooper Union, Columbia, City College, and elsewhere. And we also have a number of very talented high school students who rotate with us, one of whom is currently a candidate in the Regeneron Science Talent Search in this cycle. What do these students do? What are they exposed to? There are a number of different axes that we work on. One of them is related to developing, prototyping, and licensing new devices that initiate within the Mount Sinai ecosystem. Often they're surgeon-initiated ideas. This is one of them that is slated for a first-in-human later this year, early next year. We are also very actively engaged in a number of industry collaborations designed to simulate, test, and educate surgeons in the use of new devices or in the fixing of devices that are in the pipeline of development. And setting up these simulations, analyzing the data, and working with the whole system is very interesting and challenging, and provides really terrific educational experiences for residents, fellows, medical students, and young engineers, all working on different angles of the problems. And of course, we've spoken in the past about the work we do launching startup companies around the technologies we incubate, and these have emerged from a number of different areas, including orthopedic surgery, in the area of advanced robotically fabricated personalized replacement joints, in the area of skull-based surgery and head and neck surgery, and in the area of cardiovascular surgery, also in innovations around minimally invasive mitral valve repair. We have a large number of industry collaborations. Here's just a short list of some of them we've been working with over the last 2 years, both on translational work together with industry in engineering research services type arrangements, clinical trial design, and of course, technology licensing in the biodesign pipeline. And I owe this slide to Turner Baker, who really pointed out that the educational experience here at Mount Sinai is really unique for many reasons, including that the entire device development pipeline can be found in one single building here at Mount Sinai Hospital. On the 0th floor in the basement, we have the Rapid Prototyping Center, where some of the ideas get bounced around, developed, simulated, prototyped, iterated on. And then, of course, we have both hands-on work in and around the operating suites and clinical trial work in the operating suites, and animal preclinical work up on the 26th floor. So it's a really amazingly efficiently condensed place, and really a very, very rich opportunity for education in device development. And I'm really glad to see that we have our colleagues, Dr. Evan Flato and Dr. Lisa Galitz, here with us in Ground Rounds this morning from orthopedic surgery. This year was a really very significant year for biodesign. We want to, with Dr. Flato and others across the Institute, we won a grant from the New York City Economic Development Corporation, the Life Sciences Infrastructure Grant, to really expand the work that we're doing in biodesign across the institution with many collaborators in some of the areas that I just described. And I really do hope, I know we all hope, that the educational mission will be further advanced through this grant and what comes next. Sinai Biodesign has graduated 3 PhDs now, 2 of whom you already know well, or this department knows well, and one of whom, if you don't know him, you'll meet him this morning. Turner Baker is now on the faculty of our department, as well as in population health science and policy. He's been really a force in biodesign and across the institution. And Fred Kwan is a very, very promising researcher in artificial intelligence as applied to radiology. A number of cover journal articles over the last couple of years in areas of radiology and artificial intelligence, and will be applying to radiology residencies in the coming cycle. And it's really my pleasure to introduce this morning Joe Borello. It's hard to find a better way to illustrate some of the activities that we are doing in education through biodesign and across the institution in medtech innovation than by really giving the floor to a rising star. By way of introduction, Joe is a newly minted PhD from the Graduate School of Biomedical Sciences here at Mount Sinai. And during his years here, he has had a really substantial impact on the local ecosystem of makers and entrepreneurs. Joe graduated cum laude from the Macaulay Honors College at City College of New York in 2014, where he majored in biomedical engineering, specializing in material science. And he became interested in translational research during his undergraduate years. And one of the things that he has continued to contribute to the Mount Sinai ecosystem is his experience in the I-Corps program, which many of you know is a feeder bootcamp program for technology innovation into the National Small Business Initiative ecosystem. Joe won awards during his undergraduate work for entrepreneurship and was recognized as a super user of the Zahn Innovation Center at City College, where he still holds an advisory role. And I know they would love to have him back on faculty if we let them. After graduation, Joe spent a year working for 3D Systems, which was and is a leader in manufacturing industrial grade 3D printers. And with that experience, he came to us. He came to the Mount Sinai PhD program with industry level experience in 3D printing, just as the field was really heating up. And he proposed an idea of using advanced manufacturing techniques to create novel metamaterials, which he'll tell us something about today, with specialized properties designed for advanced surgical repair applications. That was a joint project between the laboratories of Dr. Kevin Costa, who I think is with us this morning, and Dr. Jun Qian Xu. And at that same time, Joe helped to establish the new version of the Rapid Prototyping Center at Mount Sinai, which became Mount Sinai Biodesign. And we're very privileged that he carried out and continues to do some of his doctoral and further work here within Biodesign. Joe collaborates broadly within and beyond Mount Sinai. He's a natural connector, and he's mentored and taught many junior students across the institution and at our neighboring institutions, including Cooper Union, City College, and Rensselaer Polytech. There's a lot more that I could say, but really I want to hand the floor to Joe this morning to discuss his ongoing work pushing the boundaries of 3D printing and additive manufacturing, combining computational and experimental methods to study the unusual properties of auxetic metamaterials and to develop a platform for mechanically optimized graft and implant materials in a number of surgical fields, including neurosurgery, orthopedic surgery, and cardiothoracic surgery. And without further ado, it's really my pleasure to introduce Joe Borello.
Great. Thanks so much, Ben, for that introduction. And thank you, Dr. Morgenstern, for this invitation. And thank you to Margaret Hanley for helping organize all of this and sending me the links that I need. So I believe everybody can see this now. I'll jump into it. I do have one quick disclosure. As Ben mentioned, I'm a co-founder, former CTO, and current consultant for Biosapien, which will be briefly mentioned in this presentation. And so Ben already gave a little bit of a background to me, but I want to reiterate, what I've been up to for the last 10 plus years. Academically, I got my bachelor's in biomedical engineering from City College, and shortly thereafter I came to Mount Sinai, first working in the Rapid Prototyping Center and subsequently also becoming a PhD candidate. And really, right at the start of my academic career, I also began my entrepreneurial career in the Zahn Innovation Center at City College, which I've leveraged to get some of my first industry jobs in the technology and advanced manufacturing sectors, like Ben mentioned, and also several instances of startups, each of which leverage in their own way advanced manufacturing technologies and material science, which have really been a thread throughout my entire academic and professional career. And I say all of this to highlight this unique intersection of advanced manufacturing and the biomedical sciences, where I've been fortunate to kind of reside in the middle for the better part of a decade. What this led to was the foundation of my thesis research and really what I hope to be my career research moving forward, which is that the body is a dynamic environment. I don't think I need to emphasize that too strongly to this audience. But I think notably, the things we implant into the body are very frequently not dynamic. They're static pieces of titanium pedicle screw or Gore-Tex mesh. And as a result, there's a biomechanical mismatch. And the scale of this biomechanical mismatch really can't be understated. There's 1 in 5 adults in the US who have some kind of medical implant. And 10% of those implants will experience failure only due to the mismatch of biomechanics with their surrounding environment. This represents an over 10 billion annual cost for revision surgeries and replacements. And so what do these biomechanical mismatches look like? I think a very famous case, a very well-known example is stress shielding in orthopedic implants, where a non-physiologic load is transferred to the stronger titanium versus the bone that should be loaded. Another common example is peripheral artery grafts, where you experience a loss in patency when you're implanting with a synthetic mesh like PTFE or Dacron, and hernia meshes, which very frequently stiffen and rupture as a result of pulling out of the softer surrounding tissue. And so the big question here is, can a synthetic material better approximate the dynamic tissue mechanics of the body? And the answer is maybe yes. Mechanical metamaterials are an exciting class of materials where the function of the material follows from its form. And so there's a couple of examples here showing a metamaterial that translates a direct push into a twist, pedicle screws that are designed to better distribute stress across their length. And I think a lot of folks in this audience are familiar with cranioplasty meshes, which are also a metamaterial designed to bend without kinking. And so this is a pretty exciting field. And specifically, for my thesis work, we wanted to look at a class of metamaterials called auxetics. So just to introduce what these are, most materials like rubber bands or other elastomers have a positive Poisson ratio. They get thinner when you stretch them. Auxetic materials counterintuitively do the opposite. When you stretch them, they actually get thicker. And this is a result of their microstructural patterning that causes the distribution of forces to expand these unit cells versus compress them. And so there's tons of different geometries that have auxetic properties. And what was for a long time an academic exercise and something that was done only mathematically, theoretically, is now being unlocked due to advances in computational design and advanced manufacturing, such as 3D printing. And there are a handful of examples currently being used clinically of auxetic metamaterials, such as self-expanding stents. And again, these cranioplasty meshes are actually also auxetic. One of their properties is to bend without kinking. What we were interested in was a new application for these auxetic metamaterials. We wanted to see if they could be used as actuators. Most of the time, auxetics are used commercially in their compressive applications. They have unique indentation resistance, which makes them appealing for a lot of compressive applications. And they have the unique ability to bend over curved surfaces without kinking, which makes them useful in a lot of wearable applications. What we were interested in was, can we use the other phenomenon, the expanding when stretched, to drive a force, to create some kind of actuation? And so I want to take a moment to break down an actuator system and how we related this to auxetic metamaterials. An actuator, of course, moves in a linear fashion, some stroke length, and it puts out a certain amount of force or work. You can push back on the actuator with some amount of force, and at enough force, you actually prevent the actuator from moving, and that corresponds to the lockup force. To take this and translate it over to an auxetic metamaterial, we built a generalized model that took into consideration the material properties, some of the unique design constraints we can impose, and applied the mechanical loading that was of interest to us, which was the stress and a force that the auxetic actuator would have to overcome. We could then characterize if something was behaving as a meiotic material, an auxetic material thickening corresponding to a stroke length, and if at a certain resistance, it neither expanded nor contracted, that would correspond to its lockup force. And so with these inputs, we could characterize a large array of different auxetic metamaterial designs. And so we did just that. We built a high throughput computing pipeline using the Open Science Grid to take all of these different geometries and all of these different input parameters characterizing the different loading conditions. And we ran each of these combinations in parallel on computers through the HTC. getting ultimately a large data set of results to analyze. And so these are a very rich design space. And I want to give a quick example of what some of the outputs of this look like. For a meiotic material, a conventional material, when we look at the amount of stretch and the amount of force the material is trying to overcome, notably, there's no region where this material gets thicker. There's no set of combinations where a meiotic material will ever increase in thickness. It has no actuation potential, which is what you would expect. If you think again about the rubber band example, rubber bands get thinner when you stretch them. In the case of auxetic geometries, there does exist a set of opposing forces and longitudinal stretches where you get a thickening of the material. So there's an actuation happening. There's also a region where there's neither thickening or thinning, and that's our actuator lockup force. And so these kinds of outputs let us screen thousands of different auxetic geometries and design combinations and identify for whatever application we're looking at, what are the best design candidates. This ultimately to validate required some custom work. And so in collaboration with both Biodesign and some of our machining equipment and Dr. James Iatridis and Phil Nasser in the Orthopedic Research Lab, we built a unique mechanical testing system to actually characterize the auxetics we were designing computationally. And so what this looks like is when we stretch, we measure these distances, and we can see if something is behaving as an auxetic or meiotic material. And fortunately, all of these results that we've obtained so far show that there's very strong correlation between what we're simulating and what we're measuring on the bench. And so this is very exciting because it means we have a pipeline that can not only screen auxetic material candidates, it's a decent approximation for how these things are going to behave in a physical environment. And so with this pipeline built, and operational, we sought to apply it to a specific clinical indication, which was passive cardiac reinforcement. And so in certain cases where damage to the heart is done through myocardial infarction or other insult, passive restraint can be applied in the form of either partial or complete patching that covers the left ventricle or both ventricles. And this serves to reinforce the heart, similar to the way a patch on your jeans reinforces the knee joint. However, these patch systems are an imperfect solution. During the pumping phase, they serve their purpose of preventing dilation of the damaged region of the heart. But during the diastolic phase, they inhibit filling, ultimately reducing cardiac output. And so the vision was, can we take these patch materials that have really not seen much improvement over the last 60 years and incorporate metamaterials in a way to better approximate the cardiac biomechanics? So can we dynamically change the thickness of this material? Can it be stiff during the systolic phase and soft during the diastolic phase? And ideally, can it also help provide pumping back to the region that can no longer beat? And so what we looked at was this auxetic actuator approach, taking a patchcraft material and instead of comprising it out of a meiotic PTFE or dacron, giving it a auxetic design so that when the heart beats, it actually transfers some of that energy into the auxetic, stretches it, and drives this actuation force. But working in theory and working in practice is not the same thing. And so how do we go from the results we were seeing from our simulation and mechanical testing pipeline to something that actually gets implanted onto the heart? How do we actually make this? To begin with, we wanted to understand how these patch materials would behave specifically in a cardiac environment. And so taking our generalized simulation pipeline and refining it to apply to a cardiac biomechanical model. And in parallel, we explored a bunch of different ways to actually make these things. To first talk briefly about the biomechanical modeling of the heart, we were fortunate to leverage a model that had been previously developed by Dr. Ana Estrada in the Jeffrey Holmes lab at the University of Virginia, where she developed a baseline ischemic and patch reinforced heart model. And so we were able to take the patch reinforced heart model and incorporate our own auxetic patch inputs that we obtained from the simulation pipeline. And then we could put this onto a beating left ventricle and get a sense of how these materials would behave in vivo more accurately and more precisely than what we could obtain from the generalized simulation studies. So our first area of interest was to see how this patch behaved in response to the surrounding cardiac forces. And so we wanted to take a look at the patch mechanics in terms of the radial strain. Looking at this model, briefly, this is all reference to the end diastolic phase. And so over the entire cardiac cycle, we go from end diastole to systole, and so the healthy heart tissue gets thicker as you would expect. In both the ischemic and isotropic conditions, you see a thinning because you're either have non-beating tissue or a meiotic material. And so in both cases, the surrounding forces of the healthy heart tissue are causing a thinning. When we incorporated our auxetic patch, interestingly, we saw a partial recapitulation of that baseline behavior. And so that was a very encouraging result. It showed that the heart was providing the right conditions to actually actuate this metamaterial. Looking also at global cardiac mechanics, we saw that compared to the baseline isotropic meiotic patches, we can, at least under certain mechanical conditions, get auxetic patches that come very close to the performance of these existing gold standard patches. So the key takeaways here was that the heart does provide enough stretch to expand an auxetic patch, which was really the big question we had coming from our generalized simulation pipeline. And the auxetic patch impact on the wall stress and global mechanics is comparable to the existing patch materials. But that was only half of the fight. We had to also figure out how to make this thing physically. Up until this point, these had all been simulated in silico with a lot of encouraging results, but ultimately needed to be translated in some form through to a physical prototype. And so we explored basically the breadth and depth of advanced manufacturing options available in biodesign and then some to try to arrive at a viable prototype. Each of these had their own trade-offs between material properties and feasibility to deploy. And ultimately, we ended up choosing digital knitting, but I wanted to talk briefly about the process we took to get there. First, we looked at SLA and DLP 3D printing, which is a form of 3D printing most known for its resolution and material breadth and depth. But ultimately, we ran into some material and resolution trade-offs. The smallest and highest resolution materials are very frequently rigid and not really biomechanically compatible with the tissue we were looking to implant it in. And the materials that were elastic enough to be viable really couldn't be printed at these resolutions. And ultimately, this is still an issue that the industry as a whole is dealing with. We also developed a new form of wax 3D printing down in Biodesign as a way of achieving higher resolution with a number of unique elastomers with desirable mechanical properties. And while this worked to produce a wide array of structures, they were all limited in their design to these two-dimensional constructs. And so this was a very interesting technique, but ultimately not applicable for at least the heart, although there are maybe other applications for other tissues where this would be viable. Another form of 3D printing we explored was fresh freeform reversible embedding of suspended hydrogels, which was developed at Carnegie Mellon University and is notable for its ability to negate the effects of gravity, essentially, which allows for higher resolution and more delicate structures to be printed. We did run into some issues around the duration of these prints and battling the environmental conditions of the lab. And so along the way, we actually ended up developing a modified version of this technique that let us produce models up to 72 hours at least in duration printing, which is required for these highly complex and structured metamaterials. We also printed some very exciting anatomical models, which I think are of interest to some of the tissue engineering groups at Mount Sinai. Finally, we went beyond our in-house capabilities, and I tapped into the manufacturing network of New York City and beyond to get involved with digital knitting, which is essentially 3D printing using textiles. And we were able to figure out some unique designs that couldn't be fabricated with any of the other advanced manufacturing technologies, specifically designs that took this stretching force and not only applied it as a stretch, but also as a shear to these materials, so that we could get a thickening effect by ribs or ridges moving over one another. This first design pass was interesting in improving the concept, but wasn't able to produce actuation. The second iteration, however, did. And so we took our learnings. We took our learnings from the first prototyping session and built a refined model that was able to, excuse me, not just expand as we expected, but even actuate. And so this is the actual knit textile. It is lifting up a nerd's box. We didn't have any standard weights, other standard weights available at the time. But it is indeed actuating. Sorry, it is indeed actuating the box. So what are the key takeaways from our prototyping attempts? SLA DLP 3D printing really isn't ready to be developed for this kind of high resolution application. Elastomer casting is interesting, and we developed some new techniques, but it's limited in its structural and design abilities. Fresh 3D printing is an ongoing effort in Dr. Costa's lab, specifically non-planar fresh 3D printing, which I don't really have time to get into here, but it's an exciting new way to achieve these high resolution structures. And ultimately, digital knitting has proved to be a success. It's something we want to continue to explore with more refined designs. And so briefly, I want to talk about the last step. As Ben mentioned, we can really go from end to end all in one building here at Mount Sinai, and we did exactly that for this project. We with a single pig model in collaboration with Drs. Kyo Ishikawa and Tomoki Sakato, developed an ischemia reperfusion model on the left anterior descending, where we occluded for 2 hours and subsequently reperfused in order to develop a large MI. 28 days later, we implanted an auxetic patch. In this case, it was an auxetic patch derived from commercially available auxetic foam and reinforced with spandex. We also implanted afterwards a PTFE Gore-Tex mesh as a control. And so this is the heart pre-patch placement post-infarct. We had an infarct size of about 10 square centimeters. And we patched about 16 square centimeters. And so this is the auxetic patch on the heart. So even though this was an N of 1 study, and we were learning a lot about the surgical approach itself, we did get some encouraging results. Looking at the PV loops for the unpatched condition, so the ischemic condition, the auxetic patch, and the meiotic patch, we see that there's a possible improvement in cardiac function. The stroke volume is a little higher for the auxetic, and the ejection fraction is a little higher. There's also less impairment of passive filling between auxetic and meiotic. And so this is encouraging data, and we're curious to see where this leads to next. The main takeaways from this, though, were that it's a very logistically difficult procedure to properly anchor this auxetic patch to the heart in the way that we need in order to create this mechanical transmission of force is very difficult. There's a lot of opportunity for both variability through surgeon and also just identification of the border zone versus the healthy heart tissue. We did see general agreement between what we simulated and what we got in vivo. And it's an interesting proof of concept model for this MI patching model and for the surgical approach with opportunities for future innovation. Beyond the thesis focus of MI and really going back to the idea that this is a design platform and approach, not something specific to the heart. We've done some short-term pivots into the other cardiothoracic approaches and also spun off into fields like orthopedics. We actually have an ongoing project with Dr. Alexis Colvin that was funded by MSIP, looking at the application of auxetics and other mechanical metamaterials for ligament augmentation devices and synthetic ligament grafts. And so it's very exciting to have kind of kicked off this new domain of research at Sinai. And I think the key concept here is the body is a dynamic place, and the materials we implant into it should be dynamic as well. And so I want to take a moment to zoom out a little bit and look at this more broadly, beyond just the work I did in the lab for my thesis and some of the work I've done through other programs and initiatives at Mount Sinai and beyond to help blend the worlds of advanced manufacturing and biomedical sciences. And I think of this as the Sinai Biodesign innovation ecosystem. I really think our group is very well positioned to sit right in between advanced manufacturing and the life sciences. We're a lab with 3D printing and advanced machining technologies, but situated inside of a hospital. And so very well positioned to tap into the huge network of other organizations that are helping grow these communities in New York City. We're a very dense healthcare ecosystem. I think sometimes we can forget just how many world-class academic medical centers exist within the bounds of this city. And we have the numbers to back that up. We are a large biotech hub, and we bring in lots of research and industry dollars to our institutions, especially here at Mount Sinai. But we're also a growing manufacturing ecosystem. And this is really the two parallel initiatives of the city and state to grow the advanced manufacturing and life sciences sector. And so I think uniquely with both of these initiatives happening at the same time, we're in an exciting position to see what happens when you take advanced manufacturing technologies and combine them with these important biomedical needs and questions. So startups like EpiBone, which is working on bone replacements, Biosapien, which is using 3D printing to produce cancer therapeutics, Monogram arthroplasty that Ben mentioned previously, and of course Synchron, also this very powerful blend of clinical need and advanced technology. One program that I'm especially proud of and got a little bit of mention at the beginning, I'm going to talk about it in the last few minutes here, is the Thrive program, which has been running now for the past 3 years. Thrive is a 9-month fellowship that is led by Biodesign in collaboration with the Conduits Group and Mount Sinai Innovation Partners, and it really takes trainees from all programs and gives them the opportunity to dive into this environment and ecosystem in a very hands-on way. Just as I've worked at developing connective tissue in the lab, I've worked at developing connective tissue at Mount Sinai also. And that's really what the Thrive program is all about, taking trainees and plugging them into this wide world of innovation that's happening here. And so we go from the needs finding stage to the ideation stage to the development stage, really following that same biodesign framework that Ben mentioned in the introduction. We take students across the academic year First, going through an onboarding and needs finding session, working in parallel with MSIP's own programming, and then come the start of the spring semester, once teams have formed and problems have been chosen, we really push everybody to get involved in milestones-driven research and development work down here. We also, reflecting the rich ecosystem that exists in New York, we try to plug everybody into as many opportunities beyond Mount Sinai as possible, whether that's I-Core programs, the NYC Media Lab, Accelerator, the Mid-Atlantic BioAngels, and engineering collaborations at some of our partner institutions like Rensselaer and College. And so there's still a lot of work to be done in this ecosystem. This is from a recent EDC report looking at the growth of the LifeSci NYC program. But I also think there's lots of groups to help do it. And I'm very excited to have been part of Sinai Biodesign for all of these years and hopefully many more to come, helping do just that with all of these organizations. And so with that, I want to leave a little bit of time for questions. I want to acknowledge the many, many people that have helped make all of this work possible. And thank you very much.
The main disadvantage of Zoom is you can't hear the applause, Joe. That was an absolutely wonderful presentation. And I think you could see why those of you who are not familiar up until now, what he's doing and what's going on, why we hope to retain Joe in biodesign, hopefully in collaboration with the Department of Orthopedics and the CCSI. Joe, I'll launch the questions with this one. In the digital printing material, it seemed that the auxetic component was dependent on a rigid component that prevented compression as you slid the two components over each other. Is that a limiting factor, that you have to have that rigid bar there that pushes it up?
I believe you're talking about this slide and these designs.
Yeah,
it's interestingly, there's still a lot about specifically this digital knitting that I don't know. This was the one domain where I wasn't the expert coming into it. These designs are a little exaggerated, I would say, in terms of what the structure actually looks like. And so these combination elastic, inelastic structures with the ridges is the exact textile that's being stretched in this GIF. And so you knit it with this pattern, but it comes off the machine pretty thin. And so these are the same kinds of techniques that are used to manufacture the existing Gore-Tex meshes and a lot of other medical textile products. And so this was one of the reasons it was so appealing to us. We could leverage the designs we were doing with our simulation system and then translate it over to a technology that was pretty well understood by the field already. And so that was our big desire here, to make this very easily translatable to the clinic.
Questions from the group? I see that Dr. Srivastava has his hand raised.
Moving him to panelist here. Well, as he's moving up, maybe I'll ask a question. Joe, that was really amazing talk. I feel like I have a good handle on what biodesign's doing, but I realize I really don't know all the amazing things going on. This is really, really exceptional. Is this something that's happening in other institutions? I feel like I've not seen this kind of organization in other institutions, but I'm just curious.
I think it happens in individual labs. Most notably, there's a group at UCLA that's interested in this kind of work also. But I think the difference is we're the only ones doing it inside of a medical center. And so even that group at UCLA, I've met some of the folks from that lab and some of the companies that they've spun out. there's this, you're always trying to get into the clinic, into the OR, and better, understand the needs of your end users. And we're here, we're right down the hall, and I think you know that as well as anyone, Chris. How often we'll bother you guys for a snippet of information that's maybe very simple and nonchalant for you, but extremely valuable for the work that we're doing. And so I think this fusion is uniquely potent in a place like Mount Sinai.
Yeah,
Chris, can you raise Dr. Flato as well?
absolutely. Yeah.
And Brandon had a question as well.
Yeah, hey Joe. I guess my question was more about kind of translating some of the theoretical materials and what we want to print and what we want to manufacture, and how do you actually take that into the next step? I know on some of the projects that we've worked on, we've had a lot of, we've talked about things that we either want to 3D print, but we don't actually have the resolution or the printers to do that. How do you find that you've been able to kind of overcome some of those technological barriers when you're in a smaller incubator type setting and not in a larger manufacturing industry, and how do we keep pushing forward when we have these ideas that we can make on the computer but not necessarily bring them to life with the current tools that we have?
Sure, thanks for that question. I think I have two answers to it. The first is related to the slide I have up now, which is the idea that when you do the design of these materials in a computational way, in a generative way, you get very, very rich data sets that have high dimensionality. And so I'm showing 3 out of 6 common metrics that we screen these metamaterials for. And so that lets you pull a lot of levers if you run into a barrier of a certain material isn't available or certain resolution can't be achieved. You can go and say, well, okay, if we cap ourselves here, what else can we adjust to maybe achieve the result we want? Because this actuation phase in this graph may look different for a different elastic modulus, and it does. So that's the first thing, is that when you use this design approach, you can adjust things. You're a little bit more flexible in terms of your iterative approach. The second answer I'll give is that I'm a big believer in leaning into the synergies that exist in our ecosystem, and if something is beyond what we can do in biodesign, I'm always looking for opportunities at the local incubators, the local fab shops, places like the Advanced Science Research Center up at CCNY that have more advanced capacities or more specialized capacities. And so, for example, the ASRC at CUNY has a New York State funded center specialized in the development of sensors. And so they've got the nano fabrication equipment and the advanced metrology equipment that you would need to develop an advanced sensing system that's just beyond what we have in biodesign. But we don't need to duplicate efforts. We have a good relationship with them, and we can collaborate with them when needed.
Thank you. Joe, do you want to stop sharing so we could see the participants?
Sure.
We're fortunate to have Dr. Flato with us this morning. Evan,
Well, that
welcome.
was a wonderful presentation, Joe. I remember being taught that a negative Poisson's ratio is a violation of the laws of thermodynamics, right? And in classic engineering, when you do unconfined compression, you have strain in a transverse dimension, but no stress. But when you have confined compression, you have a stress tensor that has out of plane stress, but no strain. And you have microstructures in your materials that achieve it. But to answer Josh's question, if you wrap a string around an elastic cord, when you pull the elastic, the string gets tight and the elastic wraps around the cord, and that's an auxetic material that has nothing stiff.
Right.
I don't know anyone using that, but the other example is fluid diffusion. I trained with Van Mao, who's head of bioengineering at Columbia, and he really developed a biphasic theory of materials. If your permeability changes with stretch, you can weep out the fluid, which also changes the volume depending on how it's constrained. And in some senses, not exactly, when you walk, you have, you have a fluid wave in the tribology of your knee joint, where you have what's called boosted lubrication, because as you compress the cartilage, you weep out this fluid. So I don't think we've exhausted the things. The final comment I wanted to make to Joe is, I'm glad you're young. I worked for over 20 years with a company that developed a way of dropping elemental tantalum on a carbon core so you could get designer material properties. And it's commercialized. We sell them now. And so you could literally match the material. The issue you raised earlier about the mismatch of material properties. So I developed a glenoid, for example, where in the shoulder, where you could have the exact material properties of bone instead of stiffening the implant, which leads to rapid wear. Now there are other technical issues, with that, but it took 20 years. I mean, safety and efficacy and pre-market, and so it's not a field for old men.
I think the simulation is a huge advance because you were able to do some of your homework before you ever tested the material.
Yep. Yeah. It was a huge boon in guiding what we actually decided to take upstairs to the ORL and test on the Instron machines. And I do think, this is where the field is headed, this kind of fusion of life sciences and engineering and computer sciences that the lines are getting blurred, and I think in a very good and productive way.
And the biologists are in there. You can put stem cells in there. You can put growth factors. It's I won't live long enough to see it, but it's going to be pretty impressive.
We have Dr. Barrow here. We're going to do a full introduction and so on. Dan, do you have any thoughts or comments on what we just heard? Hi, Dan.
Thank you so much. No, that was terrific. All I was thinking as Dr. Borello was talking is that my talk's going to be very pedestrian and much let down. That was fantastic. We have a great relationship with Georgia Tech. We have a combined biomedical engineering department with Emory and Georgia Tech, where the graduates get a degree with the imprimatur of both institutions. And so we have a lot of collaborations. Fully, I'd say probably 8 or 10 of my faculty have joint appointments at Georgia Tech. So having biomedical engineers work with physicians, I think, is a great model, because oftentimes if they don't, they go off on tangents that are interesting, but don't really end up helping human beings. So I really applaud what you're doing and working so closely with clinicians to solve real everyday problems. It's great.
Thank you. Raj, did you have something?
No, that was an accidental hand raise.
We do have a question in the chat here. Can you see that, Joe? How sure are you that 3D printing is accurate? Do you think it's completely reconstructed such that it didn't miss any minute details or artifacts of the object?
So it's this question is, my answer to this question is going to make it sound like a plant. I promise it's not. There is ongoing work in the 3D printing and really the whole advanced manufacturing field to improve the precision and accuracy of these techniques. And I actually just yesterday came across a paper that was published that is using computer vision and artificial intelligence to in situ analyze a 3D print so that it can make corrections on the fly to give you the results that you're looking for. Because that is a concern. There is a degree of error in this. There's a degree of error in all fabrication processes. But where advanced manufacturing is different from traditional manufacturing is that you do have this opportunity to plug in another computational step and kind of on the fly make adjustments that will better improve your outcomes.
And let me tell you, if you think your screws are all the same size for your implants, there's a whole field of manufacturing engineering and the tolerance bands. Like if you make a press fit implant, you have to make sure your tolerance bands overlap so that you never have an implant that's smaller than how you machine the hole. If you're going to use cement or grout, but those things are not perfect either. There's always a distribution of sizes with whether you machine it, whether you forge it, whether you cast it. Everything in biology or mechanics in implants is variable. So I would argue that the tolerances of 3D printing far outstrip the tolerances of many other kinds of manufacturing.
Well, that's great. Thank you so much. I think we'll give a couple of minutes to transition over to the Hollin lecture. And,
Bravo. Thank you for inviting me.
Thank you for coming.
Yes, thank you.
Thanks,
you.
Joe.
I think it was great to be the opener for this.
So we'll give a minute, and then Peter, do you have the intro slides?
Yeah, I'll bring them up.
Actually, maybe I can bring them up too.
I have them. I can bring them up.
Can you just send those over to me by